Hi everyone, my name is Kevin George Buhain, and I'll be explaining my COMP3132 Assignment 4. So this project demonstrates overfitting in a convolutional neural network, CNN, and techniques to reduce it, including dropout and L2 regularization, and sorry, um, and data augmentation. So the dataset that we used is CIFAR 10. Okay, so we've already run all the codes, and um, as you can see here. So first is we import the libraries, the TensorFlow, the Keras, Matplotlib, and the sklearn model. And next, we load and prepare the data by we're using CIFAR 10, and we pass it to xtrain, ytrain, xtest, and ytest. So we normalize the data by dividing them by 255. Then we split the validation data. So you can see here we have the train data. We have 40,000 images with a height of 32 by 32 width. It has the 3 as the color value. It means it's using RGB. For the validation data, we have 10,000 images, same height and width. It also is an RGB. And the test data, we have 10,000 images. The height is 32, width 32, and it is also RGB. So first thing we do is that we build our overfitted model. It has 3 convolution layers, 1 flattened layer, and 3 dense layers. The 2 dense layers have 512 neurons, and the 3 convolution layer, the first 2 convolution layers have 64 filters, while the third one have 128 filter. And for the last, the softmax dense layer only have 10 neurons. Next is we train our overfitted model. So you can see here that um, it has its accuracy starts going up after the first epoch and remains to 90% to 99% on the 2028 epoch right here. You can see it's 99.19% accuracy. That means that the model is actually overfitting. So you can see here, this the train versus validation. The train accuracy is high while the validation accuracy is low. That means the model doesn't know how to it's not good in generalization. So next we try to fix that overfitting by having a dropout layer. Sorry, yeah, a dropout model. As you can see here, we added the max pooling and the dropout. Max pooling and the dropout adds uh, a layer that helps with generalization, avoiding overfitting. Then we train our dropout model. As you can see, its accuracy doesn't jump too high. Um, at the 10th epoch, we're only at 63.03% accuracy, and on the 20th, we have a 67.6% accuracy with a validation accuracy of 70.82, which is pretty good. That means that the model is not overfitting and it's generalizing pretty well. Here is the the dropout model's loss graph and accuracy graph. So dropout regularization. Dropout randomly disables a percentage of neurons during training. This prevents the model from relying too heavily on specific neurons and improves generalization. After applying dropout, training accuracy is slightly lower, but validation accuracy improves and overfitting is reduced. So our second fix is to have the L2 regularization. As you can see here, we created our model for the L2 regularization. We use this for the L2 regularization. We trained the L2 model. So if you noticed, on the first epoch, the validation accuracy is higher than the training accuracy, and in the middle, from the epoch 10, the training accuracy is already higher than our validation accuracy, which is only 0.66.73%. And at the end of the training, we have a 78.60% of training accuracy, but our validation accuracy doesn't go higher than 71.45, and it is lower at the end of the training. So here you can notice the difference of the dropout model versus the L2 regularization model. Um, this one doesn't is not as good in generalizing compared to the dropout model by um, by noticing that we have a higher training accuracy than the validation accuracy. It means that it can, well, it's not overfitting, but it doesn't generalize as well. Here we plot the loss and the accuracy graphs for the L2 model. So yeah, L2 regularization adds a penalty to large weights in model. This encourages the model to keep weights small and prevents it from memorizing the training data. After applying L2, the model becomes less complex. Validation performance improves. Overfitting is reduced. And the last model that we're going to make is the data data augmentation model. So we will first generate the data gen. This is the uh, it's basically just flipping the images from the training model. That way, it doesn't it helps with generalization during training. Here is the this model right here is the same model as our dropout model, but we're just calling it the model augmented. And then we train our model with the augmented data. So as you can see here, we are using the augmented images for training. So yeah, first on the first training, it has a lower training accuracy but a really good validation accuracy. As you can see here, it's 33.89% training accuracy, and it has a 46.56 validation accuracy on the first epoch. On the 10th epoch, you can notice that the training accuracy is going up, but not too high. It's only at 55.24% accuracy with a validation accuracy of 63.23%. And at the end, on epoch 20, we only have a 58.81 training accuracy, but our validation accuracy is at 67.16, which is really good. That means that the actual model is learning to generalize really well compared to the other models right now. Well, if we check the actually right now the dropout model is have a higher validation accuracy than our augmented model. And then lastly, we also have the graphs of the augmented model right here. So for, as you can, if you notice here, like I said earlier, that the validation accuracy of the dropout model versus the augmented model is higher compared to the augmented model. So training with data augmentation model was trained using augmented data generated in real time using image data generator. This allowed the model to see different variations of the same images, improving generalization, reducing overfitting. The results show improved validation accuracy compared to the model trained without augmentation. So the number of epochs that we have we increase the epochs for it for the training accuracy to improve, but can lead to overfitting. So the optimal epochs are usually determined when validation accuracy stops improving. And lastly is our final model evaluation. We test the four models: the overfitted model, dropout model, the L2 model, and the augmented model using our test data. And you've noticed that uh, the accuracy for the overfitted model is the lowest, and highest would be our dropout model, with the L2 model having higher than the augmented model. Weird, but okay. Um, I think in the long run, the augmented model will always be better in generalization compared to the other models because of how it trains with more random images compared to other models. But comparison of all models, so yeah, overfitted model we have 62.63% accuracy. Dropout model is 70.77%. L2 model is 69.87%. Augmented model is 67.94%. And here you can see the final graph of our models. And the final evaluation and conclusion is that the overfitted model achieved the lowest accuracy and highest loss, confirming that it memorized the training data and failed to generalize. The dropout model achieved the highest test accuracy, demonstrating that dropout effectively reduces overfitting by randomly disabling neurons during training. The L2 regularization model also improved performance by penalizing large weights. The augmented model showed improved generalization compared to the overfitted model, although it performed slightly lower than the dropout model, possibly due to increased training difficulty by augmenting the training data. So, overall, the dropout model performed best and is selected as the final model. So yeah, here this is my assignment 4 for COMP 3132, and I hope you enjoyed the video. Thank you.